Okay, the goal of this video is to show how you could evaluate a trig function at a special angle without having a copy of the unit circle. So for example, could I efficiently evaluate the cosine of 5 pi over 4 without a unit circle and express that value as an exact answer? So hopefully I can show you how one might go about doing that. So rather than memorizing the whole unit circle, you can start identifying patterns on the unit circle. So for example, if you look at the 3 points here in quadrant 1 that I've highlighted, you might notice that there's a pattern that starting with this x value here, the numerators go 1, 2, 3, and then back up 1, 2, 3. All of the denominators are 2. And technically you can think of all the numerators having a square root. You can think of this one as the square root of 1, and you can think of this one as the square root of 1 as well. So let me hide this unit circle so that I can't cheat, and show you how you might visualize the x and y values of points B, C, and D. So if I had to label the x and y values, I might write 1, 2, 3 in the numerators of the fractions for the x values, and then I might write 1, 2, 3 like that in the numerators of the y values. As I said before, all the denominators are 2, and then simply take the square root of all the numerators. Of course, when you go to take the square root of 1, that simplifies down to be just 1, so I won't write it in that case. And again, square root of 1 right here would be 1 again, so I won't write the square root symbol. Now if I have to find xy pair for any of the other labeled points, for example, if I wanted to know the label for f, that since f is directly across from D, it'll have the same y value. And since this distance is the same as this distance, it'll have basically the same x value, except it would be negative, of course, because point F is in quadrant 2. So point F would be negative 1/2, comma, radical 3 over 2. And you can see how you could do this to label the rest of the points on the unit circle by just changing the sign on either the x or the y or both. The next thing to know is how to label each spoke, and I'm going to do this in radians. So a couple patterns you might recognize. And there's many ways you could do this, but this is one way. Notice that 4 of the spokes on my colored unit circle are red, and those would be the spokes that are multiples of 45 degrees, or in radians, pi over 4. So rotating 45 degrees is pi over 4 radians, and every time I rotate 45 degrees, I'll add on pi over 4 more radians. So if I were to go 45 more degrees, I'd have, instead of 1 pi over 4, I'd have 2 pi over 4. And then if I do this again, 45 more degrees, you get 3 pi over 4. This would be 4 pi over 4, which of course is just pi. This would be 5 pi over 4. This would be 6 pi over 4, which of course we would simplify down as 3 pi over 2. And then after 6 pi over 4, this would be 7 pi over 4. And then finally you could think of this as 8 pi over 4, which is equivalent to 2 pi. So already, if I had to evaluate, say, the cosine of 5 pi over 4 without a unit circle, I would either just label these 3 points, or if I could, just visualize those results in my head. The fact that what I'm trying to evaluate has a 4 in the denominator means that I'm going to be rotating pi over 4 radians at a time, or 45 degrees, which means I'm only going to be looking at, say, this spoke, and then positive side of the y-axis, this spoke, the negative side of the x-axis, this spoke, the negative side of the y-axis, and then this spoke, and then of course the positive side of the y-axis. So as I rotate pi over 4 radians, each time I'll be skipping one of the spokes and moving to the next. So the fact that I'm trying to find the cosine of 5 pi over 4, and you can think of that as pi over 4 added together 5 times, right? 5 times pi over 4 is the same thing as taking pi over 4 and adding it 5 times. That means I need to rotate counterclockwise 45 degrees, or pi over 4 radians, 5 times. So you could even just count this as 1, 2, 3, 4, and 5. So that means that I'm on point K. Point K must be 5 pi over 4. And then since point K is directly across point C, I could label the point for K using the same labels as point C, except since point K is in quadrant 3, both the x and y values would be negative. So I would label that point negative radical 2 over 2, comma, negative radical 2 over 2. And then of course, since I'm asking you to evaluate cosine, that would be the x value of the point on the unit circle, which in this case is no different than the y value. So my answer would be that the cosine of 5 pi over 4 is negative radical 2 over 2. So if you kind of memorize these 3 points, or at least are able to visualize them in your head, this problem of evaluating cosine of 5 pi over 4 would be reduced to simply just counting 5 rotations, moving 45 degrees or pi over 4 radians at a time. So if you're following along, the next question you might have is, well, okay, then you just showed me how to do the problem if my denominator of the angle in radians is a 4. So you should be asking, what if my problem has an angle whose denominator is a 3 or a 6? So let's look at a couple examples. Suppose I wanted to find, say, the sine of 7 pi over 6. What I'll be doing is I'll be counting by increments of 30 degrees or pi over 6 radians. So getting used to that, realize that every time you rotate pi over 6 or 30 degrees, you'll have this spoke, then this one, and then the axes always represent a spoke that you are to pay attention to, since the axes represent angles that are multiples of 30 and 45. So the ones that I'm sort of highlighting in blue would be what you'd pay attention to when you rotate, which is basically every single spoke on the entire unit circle except for the ones in red. And you can count off every time I go 30 degrees or pi over 6 radians, you're adding pi over 6 radians. So this would be 1 pi over 6. If I rotate it again, this would be 2 pi over 6, which, by the way, simplifies down to be pi over 3. This would be 3 pi over 6, which is the same thing as pi over 2. Rotating again, that would be 4 pi over 6, which is the same thing as 2 pi over 3. After 4 pi over 6 would be 5 pi over 6, which we have here. After 5 pi over 6 would be 6 pi over 6, which of course is the same thing as pi. This would be 7 pi over 6, 8 pi over 6, and of course 8 pi over 6 is equivalent to 4 pi over 3. This would be 9 pi over 6, which is equivalent to 3 pi over 2. That matches right here. This would be 10 pi over 6, which, if simplified, would give you 5 pi over 3 over here. This would be 11 pi over 6. And then finally the last rotation would be 12 pi over 6, which of course simplifies down to be 2 pi. So not that you'd necessarily label every single spoke on the unit circle if you had to do this problem. I'm just trying to give you an idea that if you had a problem where you had to evaluate the sine of 7 pi over 6, you could just rotate, like I just did, 7 times. Each time you rotate, you're adding pi over 6, and we need to do it 7 times because 7 times pi over 6 is the same thing as taking pi over 6 and adding it together, and you would be doing that 7 times. So back to evaluating the sine of 7 pi over 6, I'm going to be rotating 30 degrees or pi over 6 radians, and I'll be skipping all of the red spokes, so to speak. So every time I rotate pi over 6 radians or 30 degrees, I'll count off 1 pi over 6. So you can think of this as would be 1 pi over 6, 2 pi over 6, and you can actually even skip counting the pi over 6 in your mind to say 1, 2, 3, 4, 5, 6, 7. So this spoke here, whose label is J, must be 7 pi over 6 because I rotated pi over 6 radians 7 times. So now to find either the cosine or the sine of 7 pi over 6, I just need the labels for point J. And since point J is directly across from point B, its coordinates would be the same as these, except their coordinates would both be negative because point J is in quadrant 3. So J would have coordinates negative radical 3 over 2, comma, negative 1/2. So if you were asked for the cosine of 7 pi over 6, you'd get negative radical 3 over 2. But since the question I posed here was the sine of 7 pi over 6, of course you'd use the y value of the point on the unit circle, so that would be negative 1/2. So you could actually evaluate any of the 6 trig functions at a special angle, even if you didn't have a copy of the entire unit circle, again by just knowing these 3 points and a systematic way of rotating around the unit circle. I'd like to do one more example. So I showed you an example at the beginning of the video, what you would do if you had an angle whose measure was in radians and its denominator would be a 4. Then I just showed you one if your denominator had a 6 in it. And technically I've shown you how to do it if there's a 3 in the denominator, because I hit those spokes in the last example, they just needed to be simplified. But I wanted to show you a trick how you might go about this. For example, suppose you wanted to evaluate the cosine of, say, 5 pi over 3. You could use the same method I just did by counting by increments of pi over 6. You would just have to temporarily think of your angle instead of being 5 pi over 3 as 10 pi over 6. Just adjust the angle so its denominator is a 6. So all I did there was multiply both the numerator by 2 and the denominator by 2. So if I had to find the cosine of 5 pi over 3, I would do exactly what I just did in the last example. But since I'm counting by increments of pi over 6, I wouldn't rotate 5 times, I would rotate 10 times. So just doing that quickly, this would be 1 rotation, 2, 3, and if you get the pattern, every time you go a quarter around the circle, you're getting 3 of those pi over 6s. So you could actually go 3, 6, 9 to cut to the chase, and then this rotation here would be 10. So point N would be 10 pi over 6, and I forgot to hide my cheat sheet, but 10 pi over 6 simplifies down to be 5 pi over 3, and that indeed matches over here on the unit circle. So then, since point N has some symmetry properties related to point D, right? Point N is the same thing as point D, except moved directly down. So it'll have the same X value, and it'll have almost the same Y value, except negative. And that's because this distance here is the same thing as this distance here. So they'll have the same Y value, except it'll be negative since we're in quadrant 4. So the point here on D, I will make those the labels for point N, except change the sign on just the Y value. So of course, if you wanted the cosine of 5 pi over 3, that would be 1/2. If someone were to ask you for the sine of 5 pi over 3, of course, you would just use the Y value, and that would be negative radical 3 over 2. So hopefully that helps. If you're in a situation where you had to evaluate a trig function at a special angle, in this case in radians, even if you didn't have a full copy of the unit circle, you may be able to picture a blank unit circle and their spokes and be able to count as you rotate to the desired spoke and hopefully be able to label the coordinates correctly.